Okay, so let's go ahead and continue with our notes. Oops, wrong set of notes. Here's our notes. All right, so we stopped over here at SiO2. Now we're at BH3. So let's go ahead and let's continue. Again, I understand that this is not an easy concept and it may sound like a foreign language right now with what I'm saying. But after a while, it will start to make a little bit more sense. Okay? In class, maybe then if you have some more questions, ask me so that way I can help you out. I want to be able to help you out the best I can. But I think here, as well as the video notes, are going to help you. And when we talk about it, hopefully then it really starts to make sense and come together. Now, BH3. What do we do first step when we want to do the molecular drawing? This is molecular drawing. Okay. First, I'm going to go write down all of my atoms. I have one B because there's no number behind it. I have three H's. 1, 2, 3. That's what the 3 represents. What do I do next? I go to the periodic table and I look at it and I see that B is in group 13. So that means that it has 3 valence electrons. H is in group 1. So there's 1 here, 1 here, 1 here. I add them all up. And what am I adding up? I'm adding up the valence electrons. So 3, 4, 5, 6. 6 valence electrons is what I'm going to have total. Okay. Now don't forget, all atoms want to achieve the octet rule and get 8. There's a few exceptions to the rules, and we said that on the previous page. Let me turn my page so that way you can see it. Here's my exceptions. Boron, which is a B, he has to have 6. Hydrogen, which is an H, has to have 2. But total, we have to have 6. So I've got a boron here. And the max he has to have is going to be 6. He can't have any more, okay, and any less. Hydrogen is going to be at 2. So let's go ahead and let's look at that. How can we do that? First thing is we've got to decide who is going to be what we call the central atom. Our central atom is, when you look at the periodic table, it's the one furthest to the left. Now, boron, okay, is here, and I understand that hydrogen's over here. It's more left. But what do we say in our notes? We said that hydrogen will never be a central atom. It can only be what we call terminal atoms. It's the ones at the end. Boron, then, in that case, is going to have to be our central atom. What's the next thing in our notes that it says? The next thing is that it likes to be even. Okay, symmetrical was the word I think it used in the notes. Now, why does it want to be even and symmetrical? Because when it's uneven, it takes more energy to kind of hold it in that uneven spot versus if everything's symmetrical and even. Yes, it's still going to take energy, but it's going to take less energy. Okay, so I've got boron and I've got 3 hydrogens. So I'm going to go ahead and I'm going to put a hydrogen, a hydrogen, and a hydrogen. And I'm going to go ahead and separate that and try to keep them symmetrically even. Okay. Now, what's going to happen? These are nonmetal and nonmetal that are bonding together. And what happens? They pretty much are going to have some kind of sharing going on. So let's share here, and share here. And each line represents 2. So let's just look at the boron only. Cover up the others. 1, 2, 3 lines. So this line represents 2, 4, 6. How many electrons or valence electrons does boron need to have to be happy? He's happy at 6. Hydrogen, let's cover up this hydrogen. He has 1 line touching him. That means 2. How many does hydrogen need? He only needs 2. Let's look at this hydrogen. He has 2. And this hydrogen has 2. But how much total? 2, 4, 6. What was my total here? It was 6. I'm happy. All of my atoms are happy here when they come to bonding, as well as I used up all 6, 2, 4, 6, when it comes to this bond that occurred here. Now, the question here says the number of atoms bonded to the central atom. Well, here is my central atom, and I have 1, 2, 3 atoms bonded to the central atom. And then it wants to know the number of lone pairs on the central atom. This would be a lone pair, but that's not the central atom. This would be the central atom. If I had two dots here or here, then it would be a lone pair on the central atom. If I look at boron, do I have any lone pairs on the central atom? No, I do not. Now, this actual shape is what we call triangular planar. And again, we're going to talk about the polar, non-polar when we get to the next page. The bond angle is 120 degrees. And again, this will make a little bit more sense later on. I think there's a couple of videos that we need to help, that we can watch. That computer lab will help a little bit once you get a visualization. But what they're trying to say here is, for an example, between here and here, let me try to find a different marker. Between here and here, that's 180 degrees. Between here and here is 180 degrees. Between here and here, or between here and here, or between here and here is about, give or take, 120 degrees. And that's what the bond angle means. Okay? That's about 120 degrees. Now, again, this is really hard to visualize because you're looking at it on a one-dimensional flat piece of paper. But if this was a three-dimensional object, okay, then hopefully it would be a little bit easier. The computer lab, you'll see it in a three-dimensional form and you can rotate it. And we've got some videos that we're going to watch later on. I think is it this week, next week? And it's going to help you as well to just kind of get you a visualization. Let's keep going. Carbon and chlorine. All right, I've got 1 carbon and 4 chlorines. What do? First step, I'm going to go ahead and put carbon, chlorine, 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 chlorine. Those are all my atoms that are going to be doing the bonding. What's going to happen? Well, I have nonmetal, which is going to be doing what we call covalent bonding or sharing. We need to go to the periodic table and find out what group they are so that way we can see the number of valence electrons. Carbon's in group 4. Chlorine's in group 7, so 7, 7, 7, right? So let's go ahead now. We're going to add them all up because we want to see how many valence electrons total we're going to be working with. And why is it the valence electrons? Because that's where the bonding occurs. 5, 10, 15, 20, 24, 25, 26, 27, 28, 29, 30, 31, 32. So I got 32 as my total, okay? Let's go ahead and let's look. First thing is we need to figure out who the central atom is going to be. Normally, if you have one element that's just by itself, that's probably going to be the central atom. We've got carbon. And remember, we said in our notes on the previous page that carbon will always be what we call a central atom. Since there is a 1 carbon, well, let's go ahead and start off right there as carbon as the central atom. We have 4 chlorines. Now, what do we know from our notes on the previous page? We know that we want to have our, what do you call it? So we want to have our bonds, or we want to have our atoms when they bond together to be as symmetrical and even as possible. So how can I make 4 chlorines even? 1, 2, 3, 4. Chlorine, 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 chlorine. Okay? Now, let's go ahead and we need to add the rest of our electrons. This line represents 2, 2, 2, 2. So 2, 4, 6, 8. That means that we've already used up 8. So 32, take away 8, comes out to 24. We have 24 valence electrons left. Now the next thing is we know that carbon himself wants to achieve the octet rule. All of the elements want to. And so for them to achieve the octet rule, they have to have a total of 8 valence electrons. So let's go ahead and cover this up. Let's count the number of valence electrons or electrons that are attached to carbon. This line is 2, 4, 6, 8, because each line represents 2 electrons. So if carbon already has 8, can I get some of these dots and add some to carbon on the outside? No, because he already has 8. He cannot hold any more. So where am I going to do with all the 24 other dots? I'm going to attach them to the chlorine. Because look at this chlorine by himself. He only has one line, so that means he only has two. He needs 6 more electrons so he can achieve his octet rule of 8. So let's do that. 1, 2, 3, 4, 5, 6. I've got 24 to use. Okay? If I use 6 right here, so minus 6, 24, that's 18 left over. Now this chlorine also only has 2, so let's go ahead and give him some more. So I have 18 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now I used up all the electrons, okay? Minus 18. I'm at 0. Everybody is as far spaced out as possible. And why do they space out? Because if this is an electrons and these have full electrons, if I had them so close to each other, electron and electrons, negative and negative are going to try to repel. That's why they spread apart as much as they possibly can. Number of atoms bonded to the central atom, 1, 2, 3, 4. The number of lone pair, is there any? Those are lone pair electrons. Are there any on the central atom? Because that's what this is asking. No, there is not. This looks kind of like a cross. Remember though, we're looking at it on a flat piece of paper. And the one that looks like a cross like this is what we call tetrahedral. We'll talk about this section later. And the degrees is 109.5 degrees. Now let's talk about that really quick, okay? Because from chlorine to chlorine, they're about 109.5 degrees away from each other. Now when you look at it like this, doesn't this look like a right angle from here to here? And in your mind, if you're thinking it looks like a right angle, then you would probably think, oh, isn't that 90 degrees? Again, no. You're looking at it on a flat, one-dimensional piece of paper. If you were looking at it three-dimensional, in that case, then it would be 109.5 degrees away from each other. Okay? So from here to here is 109.5 degrees. It is not like this. When you look at this and it looks kind of like a right angle, it's really not. It looks like that only because this is a flat piece of paper. Let's keep going. Ni3. Okay, so step number 1, let's write it out. N, I, and how many I's? I have 3 of them. Alrighty, so step 1, we wrote down all of the atoms in our bond that we're gonna have. 1 N and 3 iodines. Then step number 2 is to go to the periodic table. Nitrogen is in group 15 and iodine's in group 7. Now we're going to add up all of those valence electrons. 5, 10, 15, 20, 2, 4, 6. So 26 is the number that I'm going to work with. We need to decide who is going to be the central atom. I've got 1 nitrogen and I've got 3 iodines. Remember the rule. When you look at the periodic table, whoever's furthest to the left is going to be the central atom. Here's iodine and here's nitrogen. Nitrogen is further left than iodine. But, here's the but, also, if I only have 1 nitrogen, then that's probably going to be our central atom. Okay? That's just a clue also. So let's go ahead and draw this in for nitrogen. And what do we do next after that? Next is we try to make sure that all of our other atoms are spread apart and as symmetrical as possible, right? So in that case, we would do 1, 2, 3. And we would say iodine, iodine, and iodine, right? Now let's go ahead and let's stop. Nitrogen still has to have 8 valence electrons. So it could be happy. Let me cover this up. How many valence electrons does nitrogen has? 2, 4, 6. Well, wait a minute. He only has 6. He needs 2 more so he can have 8. So what do we do then, Ms. Munson? Well, since we don't have any more atoms to bond to the nitrogen, then what we do is we're going to have to do what we call the lone pair of electrons. We're going to have to do 2 dots onto the nitrogen so that way he can have 8. But here's the but. When you tack in a lone pair of electrons to any of those, for an example over here, those electrons plus the lone pair is very, they're very strong. When you have two electrons like that, not in a line, but the little dots, they're extremely strong and they repel they have a lot of strength. They're very strong and they're going to repel. Now, when we add those two dots here to the nitrogen, they actually, let's go ahead and do this. It's not going to look like that. It's going to look like this. Nitrogen with the two dots, iodine, iodine, and iodine. Those lone pair electrons are so strong they shove those iodines out of the way. Okay? Now, let's go ahead. Nitrogen has 2, 4, 6, 8. He's happy. So 26 minus 8, we're down to 18. Okay, so let's go ahead. What about the iodine? This one only has 2, and this one only has 2, and this one over here only has 2. So they need some extra dots for electrons. So let's go ahead and do that. 2, that's what this line stands for. 3, 4, 5, 6, 7, 8. Okay, we got to get to 18. Let's look at this one. 2, 3, 4, 5, 6, 7, 8. Okay, this one represents 2, 3, 4, 5, 6, 7, 8. So when I count them all up, that's 18. Alrighty. And I'm used up all of my valence electrons. Remember, my magic number was 26. All right. So now let's go ahead and look. What is the number of atoms bonded to the central atom? 1, 2, 3. Is there any lone pair of electrons attached to the central atom? Actually, yes, there is. There's one. And they're asking you next, what is the name of this shape? This shape is triangular pyramidal. Again, we're going to talk about this later. Well, what is the degrees? This is also 109.5 degrees. Okay. Let's keep practicing and let's do this again. And make sure you got all the information down. H2O. Okay. H2O. What do we do? Step 1. HO. Okay. Hydrogen is in group 1. Oxygen is in group 16. Add them up. 6, 7, 8. 8. Alrighty. Now let's go ahead and do our molecular drawing. We did step 1. Step 2 says, well, let's decide who the central atom is going to be. Well, remember, our rules say that hydrogen cannot be a central atom, so it has to be the oxygen. Oxygen. Now let's go ahead and let's attach the hydrogens. What does our next rule say? It says that when we place the other, remember, those are called terminal atoms around the central atom, that it wants to be as even as possible, as symmetrical as you can. So let's go ahead and do one line here for hydrogen and one line here for another hydrogen. That's symmetrical, right? Now, first thing is, after we do that, the next step says all of your central atoms, or all of your atoms, need to have the octet rule achieved, which means 8 valence electrons, except for hydrogen, which is 2. So let's count it up. This hydrogen has 2. He's happy. Do not add any dots to him. Let's look at this one. Let's cover it up. This hydrogen has a line. That line represents 2 valence electrons. He's happy. Do not add any electrons to him. But the oxygen, he has one line here, 2, and the next line here, 4. He needs more, right? And so since he needs more, we're going to put some more dots here. All right. How many total, when we count up all the lines and dots, we should have 8 used up. And right now we only have 2, 4. So we need 4 more. What's going to happen is we're going to put a dot here. What did I tell you with our dots? Oh, it spreads out. It's already spread out. Here's the but. The other but is that we need to add 2 more because this oxygen has 2, 4, 6. We need to have a total of 8 for the whole thing to bond together. So what happens is we actually add another set of 2 more lone pair of electrons. But imagine this as a 3D model. Those extra 2 electrons actually go in the back of this oxygen atom, behind it. And when it goes behind it, it moves those other 2 hydrogens out of the way. So now they're no longer going to look symmetrical like that. That's the reason why every single time you look and you've seen H2O, it looks like this. H2O. And the reason why is because we have 1, 2 pairs of lone pair of electrons that are attached to it. Truly, again, this is flat piece of paper. So I did 2 here, 2 here. But in real life, 1 is going to be on the top and 1 is going to be in the back of that oxygen atom. And they shove the hydrogens downward like this. Now, what about the number of atoms bonded to the central atom? 2. What about the number of lone pair of electrons attached to the central atom? 2. We call this bent, this shape. And we'll get to this part later. And that's 120 degrees. Okay, 120 degrees. Kind of look at this though. Do you see how this is kind of bent downward at an angle and at an angle? Look at this one. It's also, let's cover up that H. Do you see how this is bent like that? And what is the degrees for this one? 120 and 120. Okay. No, it's not called bent. And it's not called bent because it doesn't have all these lone pairs attached to the central atom. Okay. But if you look at the shape, again, we're having to look at it on a piece of paper, which makes it a little bit more harder versus a 3-dimensional shape. Let's keep going. The next part here, let me zoom out a little bit, is what we're going to talk about: polar covalent and non-polar covalent. Okay? So, it says here though, that polar covalent bond is a covalent bond. And remember, what does the word covalent means, or covalent bond? It's when they actually share valence electrons between a nonmetal and a nonmetal, in which the bonded atoms have an unequal attraction for the shared electrons. One atom hogs the electrons in a shared pair. Kind of like that oxygen. He had 2 of them that he was like holding on, and so the oxygen was so strong he was holding on to more electrons on him. Okay, so what happens here is we end up with uneven charges on that bond, and when this uneven charges occur, they have a positive and a negative end on let me hold up, pause for a second. Negative and positive ends, or we call them charges, right? Charges on the bonds, or on the molecule. Okay, it's uneven. One side of that molecule is a little bit positive and the other side is a little bit negative. Why are they a little bit positive and a little bit negative? Because one side has more electrons, hint, hint, and it has that end of the bond is a little bit more negative, and one side still has electrons, but they're not evenly spread out and dispersed. So since they're more on one side shoved to the other end, this end now is going to be a little bit more positive, and this end will be a little bit more negative because they're not evenly dispersed. because of those lone pairs. So let's go ahead and let's look at this. You use this chart here to decide whether or not it's going to be a non-polar covalent of what we call a polar covalent or ionic bond. Okay, ionic bond is literally they don't share. My side is positive, your side is negative. Okay, I gave up electrons, you took my electrons. And so it is very opposite, meaning it has a positive and a negative end on that molecule that has the bond. Okay, polar covalent means that, yeah, it's covalent, means that it's two nonmetals, but it has that positive and negative end on it. Why? Because the uneven sharing of the electrons. And nonpolar means that it's nice and dispersed evenly. Okay? Now, how do I figure this out? We look at the numbers. It goes from 0 to 3.3. Okay? This is where this chart comes in place now. Okay? It says calculate the electronegativity difference. Remember we talked about that in the last unit? Between the following two ions. Then determine if this is an ionic bond, a covalent bond, polar covalent or non-polar covalent. So for an example, what about when hydrogen and sulfur bond with each other? So let's go ahead and let's look at hydrogen. He's over here. I'm going to put 2.1. Sulfur is a nonmetal, and so sulfur is 2.5, which is right here, 2.5. We actually look at this, find the difference. The word difference means to subtract. Now, when you subtract, we're not looking for a positive and negative. We just want to find the difference. So let's subtract it. And I end up with a difference of 0.4, okay? Don't give me negative 0.4, just 0.4 is the difference. Let's go to our chart over here. Where is 0.4? 0.4 is going to be somewhere about right above 0.3, okay? So what do we call it? Do we call this a, is it going to be polar or is it non-polar? Non-polar is going to be right at that 0.3 and below. Is non-polar. Anything above, it starts to become polar. What does that polar mean? It has a positive and a negative charge side to that molecule. So it's right above it. We're going to call this one polar. What happens is my hydrogen here and my sulfur is over here. This bond together is going to be what we call a polar. Is it very polar like over here, like ionic bonds? No, it's barely going to be polar. It's right above that line. But when I look at the hydrogen and who's right over here, and I look at the sulfur, whose number is bigger? The sulfur's number is larger. So that means that actually the sulfur pulls those lone pairs or pulls those electrons from the hydrogen a little stronger. Imagine if there was tug of war. We had a sulfur atom and we had a hydrogen atom and they had a string between them, right? And they're pulling tug of war. Sulfur is a little bit stronger and so it has more of the string pulled towards it. It's caused hydrogen to come a little closer to him. Okay, let's try it again. The next one is cesium and sulfur. Cesium is CS. Where's CS? CS. Somewhere's over here. CS. Right here. CS, 0.8. So I'm going to put right here 0.8. Sulfur is a nonmetal, which is 2.5. 2.5. Okay. Let's go ahead and find the difference. Nothing about a negative value. Just give me the difference, which is 1.7. Okay, on your calculator. So I've got CS and I've got sulfur. And 1.7 is my number between those two when they bond together. 1.7 is right over here. Okay, is that going to be polar or non-polar? Definitely going to need to be polar. So we're going to say polar. And which one is stronger? Who is going to be doing the pulling towards it? Is it the CS? who is 0.8, or is it the sulfur, which is 2.5? Sulfur, 2.5. So it's going to pull in that direction. Okay. Chlorine and sulfur here. All right. Chlorine's over here, a nonmetal, who is 3.0. Right here. 3.0. Sulfur is a nonmetal, which is 2.5. Find the difference, and that's 0.5. All right, chlorine is Cl, sulfur is S. Alrighty, who is going to be doing the pulling? Who is stronger? Chlorine. So it is going to pull sulfur a little closer to him. 0.5, look, 0.3 is that number. Anything above 0.3 is going to be considered polar. Okay, so this is going to be a polar. It may not be very strongly polar, but it's still a polar. Alrighty, so hopefully this makes a little bit more sense. We've got some practice over here to do in just a moment, but I think we should go back now and let's look at this. Now, we left that whole column blank. Another way that I can kind of quickly just estimate whether or not it's going to be polar or non-polar is going to be the shape of my molecular drawing. So when I do my shapes and my drawings, if I see that it's nice and smooth and even all the way around, look at that nice flat line, because nobody's pulling, look at this, there's no pulling towards them, then that's going to be an indication that we call this non-polar. The drawing is a great indication of what it's going to be polar or non-polar. Let's look at nitrogen. We can go back and do the math. We can go to the next page, go to nitrogen, who is 3.0 right here. Oops, sorry. So 3.0, take away 3.0 ends up being a 0 value. Anything below 0.3 is non-polar. So 0 is definitely less than, but if you look at the shape, it's a nice straight line. It's not bent or kind of pulling towards anything. So we're going to call this one non-polar. Okay, what about the next one? Again, I can do the math, but when I just look at it, I can see that it's a nice flat line. There's no one atom pulling stronger to it. So again, it's non-polar. Let's look at this one though. Alrighty, so we might have to do a little bit here. I do see that we have not only boron, but we have 3 hydrogens. But how are the hydrogens arranged on this molecular drawing? They're actually all 3 even,